Okay, looks like the line is almost ending. Dave, is there something you wanted to say? Oh, wait, we will get to you eventually. So we just heard an excellent ITC colloquium by Silvia Toonen. Where is Silvia? Oh, here she is. Very interesting and educational, and we learned a lot about the origin of type 1a supernovae. Presumably we now understand perhaps where they come from. Silvia will tell us about something else soon. We'll start with our own Dave Latham, that will talk about the search for habitable planets. And we'll move on to the CFA colloquium speaker today, Vikki Meadows, from the University of Washington over there, that will also talk about exoplanet biosignature assessment, so that's sort of complementary. Then we'll hear from Silvia, that is visiting us from Birmingham, and she will talk about the fault in our stars, stellar mergers, and age estimators. And then finally we'll conclude with a person that many people remember, except he grew a beard. He used to be a graduate student, Nick Stone, in our department, a long time ago, and recently he accepted a faculty position as an assistant professor at the Hebrew University in Jerusalem. He will speak about a statistical solution to the non-hierarchical three-body problem. Dave, go ahead.
History of astronomy.
Where's the mic?
The mic's right here.
Oh, but we don't hear it.
You have to say that again.
Now you can hear me, Avi.
Yes.
We are poised to characterize rocky planets enough like the Earth that we can imagine life as we know it could be comfortable there. So I'm not talking about giant planets like Jupiter. Those are the easy ones. I'm talking about rocky planets with surfaces at the right distance from their host star so that the temperature is right for water to be liquid on the surface. And they have suitable atmospheres. The original atmosphere of hydrogen and helium is gone, long gone, and been replaced, hopefully, by a secondary, more compact atmosphere with molecules such as carbon dioxide and methane and nitrogen and water, and maybe even oxygen. So I'm going to start setting the stage for the dream that we have, the detection of biomarkers of rocky exoplanets using remote sensing, by reviewing the single most important result from the Kepler mission, which launched in 2009. The prime mission stared at one region in the sky, a big region. We know it was big because we did the observations to provide the Kepler input catalog, but it's really a very small region, only 1/400th of the sky. And the main result from Kepler is the two observables that Kepler gives you, orbital period here in days, 1, 10, a year out here, because you see the repeated transits, get the ephemeris from that. And the other observables, you see how much light is blocked during the transit. So you get the size relative to the star, and here it is plotted, the size of the planet relative to the Earth. So there's the Earth. There are the next planets that are bigger, Uranus and Neptune. You have things down here, the terrestrial planets, Venus and Earth, and then Jupiter-sized planets up there. And the striking thing is how many planets there are between the size of Uranus and Neptune and the size of Venus and the Earth. How many are there in the solar system? 0. But nature knows how to make lots of those. The other thing you notice is that there are lots of multiple transiting systems, but I won't get into that today. So I'm going to look at the histogram where we have collapsed everything onto the vertical axis, right? So the number at any given radius. Here's that histogram. Nice paper done by Francois Fressin on the team here. And you can see now numerically corrected for the incompleteness, because for transits you got to have edge-on orbits. And so you'll have to figure out how many you've missed because the orbits were not properly aligned. And you see how it's built up, 15 per star in each of these 3 bins. You add up those 15, it's like half of the stars have planets in this category for a period shorter than 85 days. But there's a shortcoming, a flaw in this diagram, and namely it is blurred out because the size of the planet is only known relative to the size of the star, and the sizes of the stars are not well known. So B.J. Fulton, in a brilliant PhD thesis at Caltech, worked that out by improving the stellar parameters using high-resolution spectra, which had been obtained to try to measure the masses for those planets. But here you see just the radius again on the vertical axis, but now it has improved resolution in the horizontal axis, and the here's the planet size. We've flopped the axis for you. That's the histogram, and you see the 2 humps here. And it was tempting to think that these would be, the dividing line would be between rocky planets, which look smaller because they don't have atmospheres to block the light during the transit, and things that might be called sub-Neptunes. But we need masses, that's sizes. And so now we need masses. Here's a diagram that I like from Li Zheng in a paper just accepted for PNAS. So now we have moved to a diagram where the horizontal axis is no longer period. It is now the mass. And there's nowhere near as many points in this diagram because it's really hard to measure masses for small planets from the Kepler sample because they tend to be very faint. So here you see compositions. The Earth and Venus are down here. So these are rocky planets with an iron core, very much like the Earth. And you see this lump here. That's not necessarily because that's where there are lots of them. That's an observational effect. Those are the easiest to get masses for. And then up here, you have things that can't be rocky alone. They have some kind of volatiles, perhaps an envelope of hydrogen and helium, perhaps some water in their composition. And in between, you see this gap again, but now in the way I think you really should look at it. In other words, are we truly separating things that have extended atmospheres of volatiles from the rocky planets? And that's where TESS is going to come in. I'm going to show you some very recent results from the TESS mission. Here is a slide that I stole from George Ricker, so I left his name on it. And here we have the distinction between what TESS is meant to do and Kepler. You see this pencil beam that Kepler observed, less than 1% of the sky, 0.25%. And now this sphere that TESS is going to search, nearby targets, therefore the brightest examples of transiting systems. And our goal is to find all the best ones for future follow-up work. And the TESS progress report, we have 9 months of data on the ground. We're in Aura Sector 10. We have follow-up observations very actively underway. I checked yesterday morning, and there are 81 published papers that mention TESS. 6 of those are from the mission reporting masses for small planets that meet the level 1 requirement of measuring masses for 50 planets smaller than 4 Earth radii. 230 non-refereed papers mention TESS. 47 of those are on archive, mission papers on archive with strong results, many additional masses. And the extended mission proposal has been submitted. That's the best thing that came out of President Trump's move to shut down the government. It gave us an extra 35 days to prepare that proposal, and boy, did we need those. But that's the only good thing that came out of it.
Were you allowed to work during that time?
No, I was not allowed to work until our director accepted me. Okay, here is a recent result. It's Test Object of Interest 402. It was released about a month ago. Oh, look at all the authors. It's just like those big physics projects. And here are two orbits. There are two transiting systems, and look at how many observations there are. You're supposed to be impressed by how agile and quick we are with making follow-up observations. If you draw that conclusion, of course, you're wrong. These were targets that were observed previously over the years for radial velocity surveys, but they couldn't find any low amplitude orbits. But once we give them the ephemeris, the period, and the epoch, they know exactly what to look for, and they pop right out, and you have an instant paper, really nice paper. And here you see these two islands of populations again. So it's planetary radius again on the vertical axis, but here it's stellar irradiation, because one of the interpretations of this is the atmospheres of the close-in planets have been evaporated, and this is a kind of evaporation gap, and these are the ones that have still maintained part of their hydrogen and helium atmosphere. That's one possible interpretation, not the only one. And here you see the two planets are in the two different populations, and the masses are almost the same, but the radii are different, and therefore the densities are different. And so these are the planets that we really want to look at to explore their atmospheres with remote sensing, because they are going to be rocky and have surfaces, and we can see interesting atmospheres. So with that, I better pass it on to the next speaker, who's going to say how we look at this. Oh, okay. All right.
Dave, according to this diagram, it seems like the separation is almost vertical between the two populations that you show us, and it's not obvious that it is caused by the relative radiation.
There are people who do the theory of the evaporation gap, and this doesn't have the right slope.
That's the question. Does it have the right slope?
It's a little early to say,
Okay.
but it's tempting to think it looks about right.
Okay. Questions? Any other questions? Go ahead.
What do we know about the evolution of these systems with time? And so, for example, in the distribution of orbital radius, whether things are actually moving in this time frame?
Very nice question, thank you. The second planet here has retained enough atmosphere to look bigger, but the models show, and you can read all about it in the paper, that it's already lost about 2/3 of the primordial atmosphere of hydrogen and dirty. It's down to 1/3. But this one down here is just a bare rock. You can't avoid it because it's that much closer to the host star, and it's just been evaporated away. Well, give it enough time and enough heat, or enough extreme ultraviolet radiation is actually the culprit.
So the idea is the rocky core of both is the same.
Yes,
It's just the next
very similar,
layer
yeah.
of gas, that's all.
Well, except the planet number one is a little over dense, and so maybe it's got more iron in the core than the Earth has. That's a bit of a puzzle right now. That may just be because we haven't measured the mass accurately enough. These are tough measurements, these masses for small stars.
Shouldn't we see evidence also for the evaporated gases as it transits?
Oh, which, yes, of course. If this is still losing its hydrogen, let's go look at Lyman alpha.
Exactly.
Yes.
So people will do that.
Yes. What hasn't been done yet. This paper was only accepted yesterday, fortunately, so I could talk about it today. But, this is the way, almost every day there's something new coming out of tests. It's really hard to keep up with it.
Problem of the riches.
Oh, yes.
If I'm reading the horizontal axis correctly, these things must be very hot.
Yes. We're not going to find liquid water on the surface of any of these. We're not going to give you the really best targets to look for habitable worlds for a while yet. This is going to be really hard.
Well, if there are no more questions, let's thank Dave again.
Here's the mic.
Oh, right. Okay, thank you. Okay, let's see what we can do with that. We can get on here. Can people hear me? Yeah. That work? Okay, great. Okay, so hi. Thank you for inviting me. I'm Victoria Meadows. I'm a professor of astronomy and astrobiology at the University of Washington, where I run the astrobiology program there. I am a card-carrying planetary astronomer, though. I did my thesis studying Venus, so I know something about hot worlds. I was asked fairly recently if I could just put something together for lunch, and so I thought, well, this is probably something completely different. So what I thought I'd do is I'd come and talk to you about how we're actually thinking in the astrobiology world about how we might assess biosignatures, so signs of life on extrasolar planets. So this talk is really a bit more of a conceptual talk, but there are, scientific results that bolster this concept. So anyway, so that's what I thought I'd do. So we have this huge question ahead of us, and Dave has set the scene beautifully. We're going out there, we're finding things that should be terrestrial planets, like the planets in our solar system. And then we have to ask ourselves this momentous question: if we get the right kind of planet and the right kind of distance from the star, how do we recognize whether that planet can or does support life? And that question turns into another question of how do we know, how can we figure out how life might globally impact its environment? Because we're not going to see that little microbe at the hydrothermal vent, we're going to see a global impact on the environment. And it turns out that photosynthesis, because it's harnessed the light from our star, is that metabolism which will produce the largest global impact on the planet. And it does that, in our case on Earth, by changing the mixture of gases in our atmosphere, by changing the reflectivity of our surface, and by also changing the behavior of our gases over time. We see the planet actually breathing in photosynthesis. So these are the sorts of things we'll start to look for, and these are what we call biosignatures. So these are astronomical signs that, life has modified the entire atmosphere and potentially surface of a planet. So we're now realizing, though, we're getting a little bit more sophisticated with this, that in the olden days, you detected oxygen in an exoplanet atmosphere, you then went to go collect your Nobel Prize, and that was pretty much, you were done. Now we realize that, of course, the universe is a little bit more complicated than that, and it might have been a bit naive to assume that only a photosynthetic organism could generate oxygen in a planetary atmosphere. And so we now realize that if we see something that looks potentially useful, we really do need to worry about the environmental context of that as well. So we're asking ourselves two main questions now in the biosignature community. How do we discover potential new biosignatures, especially those with higher probabilities of detection? So, trying to break out of just the oxygen paradigm. And how do we increase our confidence in the interpretation of the candidates that we do have? So those are the two sort of major thrusts. I'm not going to talk very much about the first one because I have no time, but I will say that one of the sort of the newest things in biosignature assessment, yes, we're going after photosynthesis, we're thinking about methane, we're thinking about all these sorts of gases that we have in our environment, but there's also a group of researchers that are now looking at something we call agnostic biosignatures, and these are sort of more like pattern matching. So this is a case where this is what I call the disturbance in the force. This is where you look at a planetary environment and you're able to assess it sufficiently well that you realize there's something in there that you can't explain. And so these are sort of examples of things that people have been looking at. Over here, the curve with the red lines through it is just an example for what we call in situ biosignatures. So maybe if we're looking on the surface of Mars, we might pull out hydrocarbons, run them through a mass spectrometer or whatever, and figure out, that's funny, they're kind of quantized in their abundance. Whereas an inorganic production of those molecules, an abiotic production of those molecules would actually produce something that was more smooth. So we could look for an anomalous pattern. And the other thing is to potentially look at the atmosphere of a planet and look at the reaction networks within that atmosphere, the photochemistry of what's going on, and look at how those reaction networks are clustered. And it turns out that the Earth's atmosphere has a very different network pattern than that of Mars and Venus. And so, again, we're kind of out on the woo-woo edge, but we're really trying to push, how do we recognize life if it's life as we do not know it? Okay, so this is something that people are currently working on. And Sarah Amari Walker at ASU is actually leading the charge on agnostic biosignature. She's amazing. Okay, and we also realize in this complicated pattern that, if we're trying to get, a planet with liquid water on its surface, there are all these parameters that go into whether or not a planet can actually get liquid water on its surface and then maintain it over time. And so we're again realizing, gosh, we are in a very complicated and complex field here, but there are bits of this puzzle that we can start to attack, and so that's what we're trying to do. So the biosignatures we're looking at are in the environmental context of their planet, which includes geological, atmospheric, and stellar processes and interactions, and as well as their evolutionary history. And we understand now that those processes can either enhance, suppress, or actually mimic the biosignatures that we're looking for. So now a comprehensive framework for biosignature identification and assessment must take into account what we call false negatives, times when there is a very strong biosphere, it's there, but the planet is suppressing that signal from getting out. And I'll just show a specific example of that. We have a fantastic example from the early history of the Earth. We're talking about trying to figure out biosignature surface fluxes. Many of you heard of this idea of a disequilibrium biosignature, that O2 and methane are not in equilibrium in our atmosphere, and so consequently that's a biosignature. That is an indication there might be a biosignature. The actual biosignature is measuring the flux of those gases from the surface of the planet. And so that's sort of an extra step that we have to worry about. And those surface fluxes, that's the production of the gas, and then photochemistry can destroy it. So when we're looking at these disequilibria, we also have to look at both the production and the destruction forces as well. And then false positives, which is something that's really come up in the last couple of years. And also Robin Wordsworth, if Robin's here, I don't know, but our very own Robin Wordsworth also led the charge on identifying one of these false positives. What a false positive is a planetary process that isn't life. Life is a planetary process, but not the one we're thinking about now. But a planetary process, abiotic, that can actually generate the particular biosignature or suite of gases that we're looking for. And we now know there are a bunch of those that have to do with the photochemistry of the star or with atmospheric escape and atmospheric loss, which is also what David was talking about. We know that planets will undergo atmospheric loss over time. So biosignature false negatives, it's a complicated plot written by a geochemist. But basically what Chris Reinhardt's trying to show here is that over the course of the history of our planet, we had oxygenic photosynthesis for quite some time, but oxygen didn't really rise to measurable quantities until fairly recently, sort of in the last potentially 800 million years. And so that is essentially a false negative for oxygen. And so the reason we care about that is that it really helps us try and decide which targets we should look at first. If we do an initial assay of an environment and we find it has a lot of reducing gases in it, a lot of methane or hydrogen or something like that, we might say, well, even if oxygenic photosynthesis was there, it may not be able to overcome the sinks for these gases in the environment. Another potential false negative might come from just sort of an observing parameter. It's not that the planet's trying to suppress it, it's just that our observational technique won't work for that biosignature in this case. And so what I'm showing here is these curves in the diagram here, mixing ratios, so abundances along the bottom, and then altitude in the atmosphere of a planet on the side. And what you're seeing is that some of these more complicated biogenic molecules, things like dimethyl sulfide and dimethyl disulfide and methyl mercaptan, are in fact very fragile to ultraviolet radiation. And so they will be concentrated down near the surface where they're produced, but they won't be sort of in the upper troposphere and stratosphere. But that is right where transmission is sensitive. Right? So if we're trying to detect a biosignature using transmission, that biosignature must be able to survive to get up higher in the atmosphere. So again, that would be a false negative. Life would be there, but we just couldn't detect it. The other thing we have to worry about is the fact that the host star can actually change how much a gas builds up in the atmosphere. And so we measure the amount of that gas in the atmosphere, and then we have to try and infer the surface flux from that. But if we don't take into account what the star is doing to destroy that gas at the same time, then we will infer the wrong surface flux. And the surface flux tells us, is this a process that could be produced by geology? Is there enough methane coming off this planet that I can explain it all by hydrothermal events and serpentinization? Or is this at such a flux level that the geology could not produce it, and therefore I'm looking at life? So on our planet, life produces roughly 200 times as much methane as the geological processes. So highly abundant methane is something we would be looking for. And so we're now looking at how, for example, different M-dwarf spectra change that. Because you can change the lifetime of a biogenic gas in an atmosphere, you can also enhance the detectability of it in an atmosphere as well. So it's now known that for planets orbiting M-dwarfs, it's probably more likely that methane will have a longer lifetime in that atmosphere and therefore may be easier to detect. Photochemistry, again, because it alters that the lifetime, therefore also changes our ability to infer the surface flux. And so this is just an example of that. So this is simulations for a bunch of different host stars for the same surface flux of all of these gases. So the planet is putting off the same amount of gas as a function of time and area. And so what we're looking at here is, how much of it does it actually build up in the atmosphere, and then what is my inferred surface flux? I can run my chemistry model backwards and say, okay, given this abundance, what do I think the surface flux is? And we see changes of factors of 10 in the abundance of the surface flux. And that could be the difference between a geological source of methane and a biological source. So it's important to know that. So I'm running out of time, so I will just skip on and just say that we also have a bunch of false positives for oxygen that we're now aware of. And these are principally the loss of oceans from planets. And if you see my talk this afternoon, I'll talk a lot about that. The loss of an ocean from a planet can produce 250 bars of oxygen. It won't hang around, it needs to go somewhere, but how much remains and for how long that remains is an ongoing question. And then there are actually photochemical aspects of that as well. That you can break up CO2 and water vapor in an atmosphere is not like our Earth's. Those can stably remain broken and actually produce oxygen in the atmosphere. The good news is that for every false positive that we find, if we understand it, we can also understand what the discriminant should be to be able to figure out what we should be looking for, what we might not see, and what we might see that would tell us that this non-biological process is working. And so I will skip to the end here then and just say that we're also looking at Venus as an example of trying to understand these false positives. So we're trying to use planets nearby to help us understand CO2 chemistry, for example, and what might happen. And I will finish with my conclusion slide. So that's just an overview of kind of where the biosignature field at the moment is working and what we care about.
So Vikki, we try to absorb everything that you told us, which is quite a lot. And suppose we pretend to be members of the Nobel Committee. And suppose sometime in the future someone reports that they detected oxygen in the atmosphere, that there are so many possible scenarios. How can, as a Nobel Committee member, how can one be confident to award the Nobel Prize for the detection of life? What would be the degree of confidence that you would give it?
Right.
Because the Earth itself had a long period of time when it was habitable and didn't have oxygen.
That's exactly right, and that is, I gave you sort of two of our main questions, but the other ones are, how do we interpret the limited data that we're getting, and how do we actually quantify our certainties? How do we tell how confident we are? And I would argue that this false positive process is actually part of that. And people, when we first discovered the false positives, people said, you are horrible people, you're raining on our parade, you're making this so much difficult. And I'm saying, no, really, this is a good thing, and here's why. Because if you detect oxygen, but you don't bother to go and look for anything else, then yes, it's always going to be ambiguous. We don't know whether it's produced by a photochemical process or geological process or life. But if you understand enough about the false positives to go through your checklist and say, okay, I went and I checked for O2 collision-induced absorption from ocean loss, I did not see that. Check. Right? So it'll be a process of elimination where we go down through each of these and ultimately come to something that is more confident than we were before because we've ruled out all the other scenarios. But yeah, ultimately, I don't think we're ever going to say definitively this is life. We're going to say we are 90% confident, and we've ruled out this scenario, and this scenario, and this scenario, and this scenario. But until they send us that modulated radio signal that encodes pi, right? that is unambiguous. That requires no environmental context. I make this joke. I mean, that could come from outer space with no known planet, and that's still a biosignature, right? And it tells us that life is there. But for anything else, for the microbes that want to talk to us, we really do have to understand the environmental context to be able to rule out these other processes.
And of course, there is the other option of visiting a place in the solar system where life exists.
Right. If we could actually go there and in situ sample and get a very close image or spectra of it, then that would be good. Right through shuttle shadow there.
There was a slide that went by very quickly that had the Earth and Proxima in terms of chemistry or wavelength. Did I see that correctly?
Yeah.
What does that imply about the two? That they're the same or they're substantially different?
So what this is showing, in this case, again, it's the same surface fluxes for the planet. So it's got Earth's surface fluxes of gases that come from both geological and biological processes. But what this is showing is that the UV spectrum of those two stars treats those gases differently. And so the UV spectrum of Proxima actually allows the methane to build up in the atmosphere. And it's not because there's less UV there. It turns out it's because there's actually less UV in a particular region that would break up water, and water produces the catalyst that then destroys methane. So it's quite a complicated cascade of things. But because of that actual slope of what's going on in Proxima, the catalyst that would destroy methane is gone, so methane builds up in the atmosphere, and so for the same flux, it's just a much more detectable signal.
Any other questions? Go ahead, Anna.
So I was wondering whether all of what you discussed today apply both to aerobic and anaerobic life, or whether there are any differences?
Yeah, so the aerobic life, the oxygenic photosynthesis, as I said, that's kind of our, oxygenic photosynthesis is the killer app. I mean, and it's killer in that it's using the star, but it's also able to use carbon dioxide and water, which is abundant all over the planet. So as soon as that was a possible thing, it took over everything. The anaerobic, so the chemotrophic folks and the anoxygenic photosynthesizers, they're a little bit harder. They tend to accelerate things towards equilibrium rather than sort of harvesting the sun's radiation to generate a very large disequilibrium on our planet. But we are looking into ways that we can do that. And so recent work by Josh Christensen Totten looking at CO2 and methane, for example. Those are two very common gases in a planetary atmosphere, but he showed that they could actually indicate a disequilibrium if the methane abundance is high enough for the early Earth back when things were anoxygenic. So yeah, we're looking into that. That's considered a harder regime, but we're definitely pushing back into that. And part of my research team's job is to go back through sort of the environments and metabolisms of the Earth and try and learn as much as we can to inform what we're going to do first.
Last question, Ramesh.
Yeah. So you said a lot about transmission spectra, a little bit about reflection. If we could get actual emission spectra from the surfaces of these planets, how much extra information would that give you?
Okay, so emission spectra are great, and I will actually talk about this in my talk later today. But yeah, transmission can be an issue because we're trying to basically find life in the stratosphere, right? I mean, we're trying to probe the upper atmosphere of a planet, not quite upper atmosphere. I get in trouble when I spoke to space physicists, but above the troposphere. That is difficult. But both direct imaging, so reflected light, and emission get us all the way down to the surface of the planet. Depends on the emission wavelength, of course. You know, we may be emitting from a higher level, but it does give us this direct beam, which in many ways can be more diagnostic because we get down to the region where life is, and life is changing the environment as it evolves. So in the emission spectrum of the Earth, we have things like ozone and methane, and you can go into nitrous oxide, methyl chloride. So there's a bunch of molecules that absorb in the sort of that thermal region. So that is a very interesting and complementary area to go look at as well. But having that direct beam is kind of important.
By the way, a lot of nitrogen oxide is perhaps evidence that there was some nuclear winter over there.
Could be, although there's some evidence that the actual nitrogenase, the process where organisms fix nitrogen, if there's a copper, if there's a lack of copper in the system, it can actually stop that process to produce nitrous oxide as the final product. So there's this hypothesis that we may have had a laughing gas atmosphere back in the Proterozoic, so that would have been pretty funny.
Well, let's thank Vikki again.
Is it on? I think so. Okay.
see if it works. There we go. Yes. So thank you for the invitation to give a talk here. So my name is Silvia Toonen. I'm an associate professor at the University of Birmingham. And I want to talk about stars that have a fault in them, that have a flaw in them. And what sets these stars apart from other stars is that they are the remnants of stellar mergers. And I think these, well, I already in the colloquium talked a little bit about stellar mergers and how they can be interesting for the transient surveys, but I think they're interesting for another reason as well. And that is, if we want to use stars as a tool to measure galactic properties, then these stellar mergers might make our lives very difficult. So for example, if you want to do galactic archaeology, or if you want to learn about the life cycle of material, then a star might look like a normal star, but if it actually comes from a stellar merger, it might have had a very different past and a very different evolution. All right. So the sample that I'm just using as an example here is one that contains all the white dwarfs within 20 parsecs. So I'm focusing on the solar neighborhood. And the nice thing about this sample is that it's likely to be completely complete. So this is based on the latest Gaia data release. And this is really a marvelous level of completeness. It still blows my mind sometimes. So this sample can be used to measure a lot of quantities about our solar neighborhood. And one of them is the ages. Now, why am I focusing on white dwarf to measure ages? That is because we have a very good method that is also cheap and relatively easy so that we can apply it to large populations. So how does this work? Well, if you have a white dwarf and you measure its mass, then that gives a very good proxy for how long that progenitor star took to go from the main sequence to the white dwarf stage. And if you measure the temperature, you have a pretty good proxy for how long that white dwarf has been a white dwarf and how long it's been cooling down. So combining these two, you get the age of the white dwarf. Now, if you take that 20 parsec sample and you look at the age distribution, this is what you get. So this is where work from Pierre-Emmanuel Tremblay from 2014. And what you see is that based on this sample, you would say that the majority of star formation actually happened relatively recently. So what I'm interested in is how do stellar mergers affect this age distribution? So as an example, if you take a 2 solar mass star, it takes about 1.5 gigayears to become a white dwarf. But if you take 2 solar type stars that merge at some point on the giant branch, for example, then it takes at least 10 gigayears to get to that point. So that merged object might give you the same white dwarf, but it actually took almost 10 gigayears longer to get there. So the question is how does that work? How often does that work? I'm going to skip through that one. So if I focus on the 20 parsec sample for a second, then it has one other nice quality. And that is that it doesn't only contain single white dwarfs, but it also contains a number of different types of binaries. So in blue here, you see the number of single white dwarfs. So it's about 3/4 of all the white dwarfs. And then there's a range of binary types. Now, the one thing that's striking here is that the binary fraction of these white dwarfs is about 20 to 25%. That is striking because their progenitors, A-type stars, F-type stars, have a binary fraction that's roughly 50%. So where has this 25% of systems gone to? And this has been deemed a missing white dwarf binary problem. And you can kind of probably already see in which direction I'm going, right? So before I get to that conclusion, I'll show you why I think that's the case. And I will support that by the modeling that I did of that 20 parsec sample of white dwarfs in the solar neighborhood. So for this reason and another couple of reasons, I try to model it, and I do that by taking single stars and binaries, a large population on the main sequence, following their evolution in time, and then seeing what kind of samples would we expect. I'm taking different assumptions for the binary evolution, for the initial binary population, for the star formation history, for the selection effects, all of those. So the ranges that you'll see are the ranges in the percentages you will see represent the difference between these models. So what I'm finding is the following.
The first thing is that the space densities that I'm finding match very well with the observed space densities. So this sample, because it's complete, has one of the most accurate measurements of the space densities. It has a low number statistics, but it's a very accurate measurement. And I'm reproducing those space densities not only for the single white dwarfs, but also for a variety of different binary types. So it's multiple populations that we're fitting in one go, so I can't tweak the population and be right somewhere and be completely off somewhere else. So that's a nice thing of the sample. The other thing that you might have noticed is that all of a sudden a new color appeared, and that's this light blue or turquoise color. And those are my single white dwarfs that are coming from mergers in the binary. So if you want to see how many single white dwarfs I'm predicting, then you should add the dark blue with this light blue color. And if you do that, then the binary fraction is in agreement with what we're observing in the 20 parsec sample. So I would say stellar mergers are common, and there's no problem of missing white dwarf binaries. So what I'm finding is that about 10 to 30% of all the single white dwarfs actually come from binary mergers. Now, at this point, one of my students, Carl Temmink, followed up on this. So this is all work from 2017. But Carl Temmink followed up on this and tried to investigate these stellar mergers in more detail. So what I want to show you here is what kind of mergers I'm talking about. So is it the merger between two main sequence stars or between two white dwarfs? And in red, you see our standard model and the other models. I would love to explain in detail what we're assuming in all of these different models, but I don't have time. So for now, just take it as an error on the estimate or a synthetic error. So what we're finding is that the most common channel is a merger between a star on the red giant branch and one that's on the main sequence. So when that merger happens, you still get a giant star out. And then that giant star evolves, and after some time, that becomes a white dwarf. So when we have a look at the age of such a merged star, then in our models we know very accurately what the age is. And we can also estimate how old would we think that star be if we would have thought that it always was a single star. So that difference in age is what we're plotting here. And you see that it can either be positive and it can also be negative. It can range up to several gigayears, but of course for the majority the difference is not 10 gigayears. Overall, we're finding that these mergers take about 1.5 to 5 times longer to form. The other thing is how much of this would you really see in a population if you want to use it to derive the star formation history. So if we try to make a model for white dwarfs in 100 parsec, take a very simple star formation history, this would be the age distribution that we would find back. If you would make this mistake for the mergers and assume, this is only for mergers, and if you would make that mistake and just think that they always would have been single stars, the age distribution that you get is this. So this is a very different, very clear distinction. Now, of course, not every star comes from a merger. So if you actually do the full model, single stars and mergers, then this is the two distributions that I'm finding. For all of the different models, it looks like this. So there's always a distinction. The effect of the mergers is always visible, but the importance of the mergers really goes up and down with how many mergers happen in these binaries overall. So overall, we're finding that the age would be underestimated by about 50 to 500 megayears. So just to wrap up, our synthetic space densities are well calibrated. Stellar mergers are common. They are important for the age measurements, and especially now that we go to this era of large-scale surveys, that sample of white dwarfs is now complete within 20 parsec, but in the next couple of years, we will get a sample that's complete out until 50 parsec. That's 15 times larger. It means that we can measure the star formation history in a lot more detail. So these things are becoming important, and it's also already being used for the stellar halo and clusters, of course. And I think I'm already way over time, so I'll stop there. Oh, yeah. Oh, really? Okay, well, then I'm just going to say that they're even more important for more massive white dwarfs.
dating the age of the galaxy or the age of the universe, and you're adding to that a little. Is that insignificant relative to the error? And the second quick question: these mergers that you're talking about, are they visible directly electromagnetically?
So the error on the age estimate of white dwarfs is usually of the order of 50 megayears. So we are in a machine that this would be larger than the systematic error just on the age estimate.
So you can see if they plump towards the age of the universe, although you stopped your plot at 10 gigatons.
Yes, because we're trying to do this for the solar neighborhood, and then that's the galactic disk is probably not older than 8 years. But we could extend it, of course. I mean, in the model, I can go to 20 gigayears if you want. Yeah.
Okay. Questions? Charles and then Rosanna.
So, first of all, thank you. This is actually really very interesting. There's a lot of information known about the statistics of separations of binary stars, and that would presumably have some impact on the probability of the merger.
Yeah.
Have you factored that in?
Yeah, so actually, so in the standard model that I assume it's a flat distribution of orbital separations, and this, which seems to be okay for like 2 solar mass stars, and this model we are assuming a log normal distribution of periods, which seems to be more appropriate for solar mass stars. So that is one of the things that gives rise to this difference in the number of mergers that we would get. Of course, the correct thing to do would be take this for the solar type stars and the other one for the higher mass stars, but we still need to make that full model and take the modeling that Rosanna and Max work.
Speaking about Rosanna, she has a question.
Well, this may already be in your model, but it seems to me that there are processes that go along with this, one of them being that white dwarf binaries can be disrupted, and so you end up having another effect coming into play. And the other is, in addition to the mergers, there are many systems where stable mass transfer may come, and that would push things in the same direction that you wanted to go, but maybe in a less dramatic fashion.
So you mean they could have stable mass transfer and then you would not know it's a binary, or it would rejuvenate the star, or?
Well, with a rejuvenation of the star, a star that gains mass as a blue straggler, basically.
Mm-hmm.
So instead of the merger to create something of higher mass, there would be an epoch of mass transfer that created something of higher mass.
Yeah. So in this 20 parsec sample, it's a sample that really has been stared at for endlessly, I would say. So that means that for those systems we do pretty well, we know pretty well if it's a binary or not. So for that, I don't think there would be any confusion. But you're right that the white dwarfs in relatively compact binaries will have a different history than a normal single white dwarf as well. The other thing you said is about disrupting binaries. Are you thinking about winds?
Well, it could be winds or it could be triples.
Okay, yeah. So here I only took binaries into account. The people of you that observed in a lot of that paid attention in detail might have noticed that green group here expanded quite a lot, right? So that's one of the populations where we do have a clear problem, the only one. And those are white, double white dwarfs. They're so white that they've never had mass transfer, which is interesting because that means that there's less knobs to turn. There's less things that happen to these binaries. So why am I over-predicting them by a factor 10? So we looked into that, and one of the things that I'm interested in is to see if they can maybe be disrupted by their own winds. Because we usually assume that winds have an adiabatic effect on the orbit. But if the orbit is very wide, then the winds are actually happening in just a very small fraction of the orbit. So it's not an adiabatic effect anymore. So the widest orbits we can disrupt. Standard wind assumptions, I wouldn't disrupt enough of them. So this is still a question. Is this initial binary population that might be different, or can we actually disrupt these wide binaries?
we need to move on. So let's thank Silvia.
All right, can everyone hear me? Well, it's great to be back at the CFA. As Avi said a minute ago, I did my PhD here sometime in the late Triassic period, but whenever I come back, it feels kind of like home again. So today I'll be talking about some recent progress that I've made with my collaborator Nathan Lee on the classical Newtonian three-body problem, which you saw briefly illustrated in that numerical scattering experiment right there. So the three-body problem is arguably the oldest open question in modern mathematical physics. It was first posed by Isaac Newton in his Principia Mathematica in the late 17th century. And in its original formulation, it asks, what is the long-term evolution of a system of three massive point objects interacting with each other solely through their own Newtonian gravitational attraction? Over the ensuing centuries, there's been a lot of analytic progress that's been made. But all of the analytic progress towards understanding the solutions of the three-body problem requires some sort of hierarchy. This can be a hierarchy in mass. For example, you can have one object that's much larger or much smaller than the other two objects, or it can be a hierarchy in orbital separation with a tight inner binary that's close to a two-body system and a wide outer orbit that also looks at the inner two objects as if they were a point mass. And in these kinds of hierarchical limits, you can straightforwardly or painfully apply the tools of perturbation theory to understand the long-term evolution of the system in an analytic way. But this is not so simple in the more general non-hierarchical three-body problem. The search for analytic or closed-form solutions to non-hierarchical three-body systems came to an end in the late 19th century when Poincaré, and soon others after him, demonstrated that non-hierarchical triples are a prototypical example of what we would now know as a chaotic dynamical system. Here I'm using the term chaotic in the mathematical sense, meaning that a small perturbation in the initial conditions can often lead to an exponential divergence in the outcomes. And it's that fundamentally chaotic nature of the non-hierarchical three-body problem that makes it so non-amenable to perturbative techniques. This is a shame because there are far too many astrophysical applications of the non-hierarchical three-body problem to list here. Three particularly interesting ones at the present day involve the dynamical formation of LIGO band black hole binaries and globular clusters, solutions to the final parsec problem in galactic nuclei, and calculation of the birth multiplicities of stars and collisional stellar clusters. So in the absence of analytic insight, most of our physical intuition about the three-body problem comes from running numerical scattering experiments, direct integration of the three-body equations of motion. And the general conclusion of many decades of these numerical integrations is that non-hierarchical three-body systems are at most metastable. They are effectively always doomed to disintegrate, and as long as the total energy of the system is negative, that disintegration is into one surviving binary star system and one escaping single star, and as you can see illustrated right there. So this is a very old problem. There are entire textbooks devoted to it. If you want to learn more, this is a particularly excellent textbook, although there is a range of others depending on the desired level of rigor. So why on earth are Nathan and I investigating the three-body problem further? The reason is that the chaotic nature of the non-hierarchical three-body problem, which for so long has been an impediment to analytic progress in finding deterministic solutions, can actually be a powerful tool if you give up on the desirability of determinism and instead look for statistical solutions. So chaotic dynamical systems are often, at least to a good approximation, ergodic, meaning that given sufficient time to evolve forwards, they will uniformly explore the high-dimensional phase space that's accessible to them. And this ergodic hypothesis is the cornerstone of the new statistical solution that Nathan and I have derived by assuming that ensembles of non-hierarchical three-body systems with the same sets of masses and the same integrals of motion, the conserved energy E naught and the conserved angular momentum L naught, are thermodynamically ergodic. We are able to compute closed-form distributions of outcome variables that we care about. For example, the angle that the escaping singleton star is shot out at, or the eccentricity of the surviving binary star system. In some ways, our calculation is very similar to a microcanonical ensemble, although there are subtle conceptual differences you should ask me about later. To be a little more precise, what we're doing is we're taking the 12-dimensional phase volume of this three-body problem. We reduce from 18 to 12 dimensions by switching to relative coordinates. So here, little r and little p are the relative position and momentum of the surviving binary, and little rs and little ps are the relative position and momentum of the escaping singleton. We look at this high-dimensional phase volume sigma at the moment of breakup in our ensemble of non-hierarchical three-body systems with identical integrals of motion. We have 12 dimensions to play with, but this is whittled down to 8 dimensions by requiring that energy and angular momentum be conserved during this process. So, for example, the total energy E naught of the system must be partitioned into the energy of the surviving binary EB and the energy of the escaping star ES. I want to point out that this ergodic formalism was first proposed by J.J. Monahan in the 1970s, but the technical difficulty of doing this integral has so far prevented any sort of closed-form solution. To be totally clear about the assumptions underlying this calculation, there are 3 strong assumptions we're making. First, the disintegration of the metastable triple is instantaneous. There's a well-defined moment of disintegration where we can evaluate this phase volume across our ensemble. Second, we're ignoring all kinds of short-range forces, gravitational wave dissipation, tidal effects. Maybe we'll think about that later, but it's not included in this equation. Third, the necessity to define limits of integration requires us to make some sort of assumption about what is the nature of the strong interaction region inside of which disintegration can occur. This is the, I think, strongest assumption we have to make, and we put in an ansatz saying that the pericenter of the escaping single star must be less than some dimensionless multiple alpha of the time average size of the surviving binary. You can think of this as sort of a causality criterion on what sorts of interactions can produce a terminal kick leading to escape. This introduces a single sort of fudge factor into our formalism. This is a one fudge factor formalism, but as we found going through the math, most of the outcomes we care about don't depend very much on this fudge factor alpha. So I'll skip over most of the technical details. The key thing we find is that the distribution of outcomes we derive is fundamentally trivariate. There are 5 dimensions in this 8-dimensional phase space that are distributed trivially, 5 Delaunay angles, if you want to be technical, with uniform distributions, and there are only 3 variables that have non-trivial distributions in the outcomes of ergodic metastable triple disintegration. You can look at sort of a simple version of this distribution function right here. So remember, sigma is the 8-dimensional phase volume we care about. We've integrated out the 5 trivial variables, and what we're left with is a trivariate distribution. Here we've written it in terms of the energy of the surviving binary, the angular momentum of the surviving binary, and the cosine of the surviving binary's orbital inclination. The integrand of this integral is the probability density function of these variables in a microcanonical ensemble of metastable triples that are disintegrating. The full solution is a little more complicated. You can gain a lot of insight by staring at it, but that's not appropriate in this talk. So let's look at plots instead. So on this plot, we show the density of states in technical language, but really just the differential distribution of phase volume with respect to the energy of the surviving binary. Here, we've normalized this energy by the total conserved energy of the encounter. So when this variable is 1, that corresponds to an escaper leaving on a parabolic trajectory and a binary that soaks up all the energy of the encounter. When it's 20, the escaper is leaving on a very hyperbolic trajectory. Shown as colored lines are the analytic predictions of our ergodic formalism, and data points represent large ensembles of hundreds of thousands of numerical scattering experiments. The 3 colors correspond to ensembles, both analytic and numerical, with different values of angular momentum. So here, we've parametrized the angular momentum in terms of the initial eccentricity in the binaries we throw single stars at in our numerical integrations. So purple is a high angular momentum ensemble, and green is a low angular momentum ensemble. We see almost perfect agreement with the ergodic predictions in the high and medium angular momentum ensemble. We see reasonably good agreement for the low angular momentum ensemble as well. I would say over the first 2 orders of magnitude in probability, it's excellent, although there's a little bit of a high energy tail that we need to investigate further. A similar level of agreement is seen if you look at the distribution of eccentricities of the binaries produced by disintegration of non-hierarchical 3-body systems. Interestingly, we see that no matter what value of angular momentum we consider, we never achieve the sort of naive theorist's guess as to what this outcome distribution should look like. We never have a so-called thermal distribution of eccentricity, which is shown as the black line right there. Instead, all of our distributions of outcome eccentricities are superthermal, mildly superthermal in the case of high angular momentum scatterings, but severely superthermal in the case of low angular momentum scatterings. And this finding, I think, is very exciting because it has quite interesting implications for dynamical formation of LIGO band black hole binaries in globular clusters, where binary formation is mediated by repeated 3-body scatterings. And in the aftermath of every scattering, you've produced a binary that draws its eccentricity from this kind of distribution. Having a strong superthermal tail indicates that it's easier to form binaries which will merge quickly with it, or at least within a Hubble time. I'm out of time, so I'll put some written conclusions up here on the board. The overall takeaway I hope you get is that the assumption of thermodynamic ergodicity allows you to write down the statistical distribution of outcomes for non-hierarchical 3-body systems in a relatively simple pen and paper way. And you can use that distribution as a tool, I hope some people do, if you are building simple analytic models for complicated processes involving many things scattering off of each other in the universe. So, thanks for listening.
Actually, the utility of your result can be expanded to a broader context because often people use n-body code, and that's used in cosmology and many other applications. And there is this fundamental, if 3 bodies are chaotic, then obviously n-body is chaotic. And the question is whether the n-body codes are actually, with the error bars that they have, whether they actually capture, statistically speaking, the correct physics, or whether they have some systematic offset. And perhaps your method can be applied to more than 3 bodies in the sense of gauging what you might expect from phase space considerations and comparing that to n-body codes. That might be very interesting.
Yeah, it's very interesting to think of extensions of this to higher n-body problems. And Nathan and I have begun looking at sort of non-hierarchical 4-body systems, as you might expect to form in binary scatterings. The map becomes a little more complicated, but I agree, when n is low, I think the same sort of ergodic disintegration argument will eventually apply. The challenge in thinking about very large n systems might be the long collisional lifetime of these systems and the fact that they don't disintegrate from pairwise scatterings in less than the age of the universe.
Ramesh?
This is great stuff, Nick.
Thank you.
So I understand this whole ergodic, chaotic assumption that you're making. But when I think of a real collision between, say, a binary and a single star, many of those are going to be like the movie you show, where it just goes round and round and round. It's as ergodic as you like. But there are surely interactions where it'll maybe make one orbit and take off. It's probably not going to be quite ergodic then. So that's going to be an outlier of some sort. But is that the source of some of your discrepancies, or is that something else?
That's a great question. Thank you for raising it, because I didn't have time to go into it. Yes, our numerical scattering experiments, only about 50% of the time undergo extended chaotic evolution. You can define a simple sort of criterion for how chaotic the evolution is in terms of a state that we call a scramble. So a scramble is a period of time where the entire metastable triple is self-bound, but there are no pairwise binaries. So this is a really strong definition of what it means to have no hierarchy in the system. Generally speaking, if there's at least one scramble, our results are in good agreement, like I showed with the scattering experiments. But I cut out the fraction of events where there are no scrambles. where instead there's a different kind of analytic formalism you can use, which is the impulse approximation. So if you have some sort of binary single scattering that just promptly resolves in a flyby or an immediate swap, there are impulse approximation arguments that give you a different sort of treatment of the outcomes.
Nick will be given another talk tomorrow at the ITC Lounge at 11:15. What would be the title of that?
It will actually be going into this in much of the detail that I had to cut out for
Everyone is
a short
invited,
talk.
come. Let's thank all our speakers.
Oh, thank you.
Way to go with this problem, right?
Yeah, it's yeah. When Nathan introduced me to this old idea of Monahan's, I thought it was just one of the most beautiful things I'd ever seen, and wanted